Hey folks, welcome back to chapter 3. We are doing probably my favorite part of the chapter today, to be honest. We are going to learn about vectors applied to airplanes. Gonna kind of learn how airplanes fly. Now, there is a big difference between this lesson and the last lesson where we looked at boats, and that is this right here. We are looking at non-right angle triangles, as you can see from these examples on the page. So there's some different trigonometry we're going to need to use. There's something called the sine law and the cosine law. And these are both equations. They actually do work for right angle triangles, but they're required for non-right angle triangles. And I'll show you how they work. Sine law is all about things being opposite. You need to have opposite angles and sides. So if you have an opposite angle and a side, sine law works great. Cosine law is what you use when you don't have an opposite angle and a side. Although what's interesting about cosine law is we're only going to use it to solve for a side. We'll just call it C in the equation like it's arranged. But the side that you're looking to solve for, that's our question mark, it has to be opposite angle C. So you still have to have opposites there. The side you're looking for, you'll always need to know the angle opposite that. And it turns out you will, the way that we do the calculations. So let me show you what these look like in practice. They're really not too bad. First triangle. I guess I'll label these things with numbers. So we'll label this one number 1 just so I can refer to the triangles by number. I always look to run sine law first. Trying to solve for side C. I don't have an angle and an opposite side where I know both of them. Here I've got an angle but I don't know the opposite side, and then I've got sides where I don't know the angle and another side where I don't know the opposite angle. So if you don't have an opposite angle and its side that you know, then I would go cosine law. That's going to work great. And what's cool about cosine law is C doesn't have to be the hypotenuse. It can actually be one of the short sides. Works just fine. So in this case, we're actually going to solve for side C. So it says C squared equals A squared plus B squared. A and B, it doesn't matter which one is which. It's just the two other sides. And that looks a lot like Pythagoras, but there's this corrective piece because it's not a right angle. So minus 2 times 8 times 11 times cosine 120. And what I'd love for you to be able to do on your calculator is actually type all of this in, stuff inside the red brackets. Do that in one step. Figure out how your calculator works so that you can do that all in one shot. Oops. So for example, it might look something like this. 8 squared plus 11 squared minus 2 times 8 times 11 times cosine 120. I'm getting all that stuff in the red brackets done at once, which gives me 273. And then we want to take the square root of that to get, oops, sorry, hiccup there. Take the square root of 273 to get C isolated. 16.5. There you go. That's cosine law. Not too bad. It's going to set up like that all the time. So let's take that value of 16.5 and add it into triangle number 2. And now I want us to solve for theta, the unknown angle. So what we've got here, I would look at that and go, hey, cool. Now I know an angle and its opposite side. I've got the 120 and opposite that is 16.5. As soon as we've got that situation, that's sine law. And I like sine law. It's the one right here. It works out really, really nicely. We can also use this pair, side 8, opposite our unknown angle. We're going to use that. We've got 4 bits of information, only one unknown, so we can find it. So sine law says this. Take the sine of an angle. I'm going to use that known pair, the sine of 120, over its opposite side. And that ratio is equal to the sine of any other angle in the triangle. like my unknown, divided by its opposite side. And then what you can do, it's pretty quick on your calculator. You can do a little cross multiply and divide. So you multiply diagonally, and then you divide by the leftover. So if we try that on the calculator, oops, shrink this down so you can see it. Sorry, there's what the calculation looked like for that first one, now that you can see it. Let's try this. Sine law 8 times sine 120. If you've got a graphing calculator, make sure you close that bracket on the angle. Divided by 16.5. I want to do that all in one step. I get a decimal. And the reason for that is that decimal is equal to sine theta. So remember, anytime we're looking for an angle, we do have to second function or inverse to get the actual angle. So second sine that answer, there we go, 24.8 degrees. So that's what sine law looks like. Angle, sine of an angle over its opposite side equals sine of an angle over its opposite side. Cross multiply, divide. Shouldn't be too bad. Triangle 3 is what we'll actually run into in the next video. It's the tricky, and I'm saying that in air quotes, the tricky triangle where I want us to solve for side x. And looking at that triangle, I'd say, hey, cool. I've got an angle on its opposite side, so I can use sine law. It's going to work great. Sine of 100 over 18 is equal to, oh, now we run into an issue. If we're looking for side x, then I need to know the angle opposite x. And it kind of looks like we've got two unknowns right now, but it turns out we don't really, because you may recall that angles in a triangle add up to 180. So this corner of the triangle, I've already got the two others, is going to be 180 in total, minus 50, minus 100. And that's going to get us 30 degrees. And that's great because now I've got that one other bit of information I need, the sine of 30, that I can use to find side x. Now what's cool is the variable we're looking for is actually kind of stuck in the denominator here, but it turns out you can still do that neat little cross multiply and divide trick. That means multiply diagonally, divide by the leftover. And since we're looking for a side, not an angle, we don't have to do any second function sine. It's just regular old sine this time. So sine 30 times 18 divided by sine of 100. There you go, 9.14, final answer. There's the tricky, again in air quotes, version of sine law. So we're going to look at some application of this math with some real airplane examples now. But before we do that, I want to go to this picture. This is just showing you that, like last day with the boaters, if we take the velocity of the plane compared to the air, that's what the PA means. So the velocity of the plane compared to the air. If we take that velocity and we add to it the velocity of the air compared to the ground, aka the wind, that's what we call air moving compared to the ground, that's going to give us the total velocity of the plane compared to the ground. Like if we were standing on the ground with our radar gun, it would be what the radar gun shows as the plane flies by. Now it turns out pilots actually have their own different lingo or specific lingo that they use. That's kind of cool, and I want to teach you this, and it's been approved by actual pilots, by the way. I have had students who are legit fly on their own pilots, and they've said, yes, this terminology works. So the velocity that the plane can go just in the air on a non-windy day, that is called the airspeed. So that's the size of that vector. So you might say, oh, the plane can go 200 kilometers per hour. So that's called the airspeed. And then the direction this vector is pointing is called the heading. And another way to remember the heading is that's the direction the nose of the airplane or the head of the pilot is always pointing. So the heading is the direction the plane points. And it turns out on a windy day, that's not necessarily the same as the direction the plane actually goes. Just like we saw with the boats that they can sort of move crooked through the water, turns out on a windy day, with a crosswind, that airplanes will fly crooked. So the heading is the direction the plane points. Now let's go and look at the wind. The speed of the wind is called wind speed. Pretty straightforward. And I don't know why, but pilots didn't actually make a fancy word for the direction the wind is blowing. They just call it wind direction. So that's pretty straightforward. We usually do talk, though, about the wind where it's coming from, not necessarily where it's going to. I will be very specific about where it's coming from and where it's going to when I give you questions, so don't worry about that. And if you add those two things together, you get the sort of actual speed and the actual path of the airplane. So the actual speed of the plane compared to the ground, that's again what the P and the G stand for, is called the ground speed. So that's the real speed once we account for the wind. And then the actual direction the airplane goes, the direction of this green vector, is called the track. So that is the actual direction the plane flies. So let's call that actual direction of flight. And I don't need you to memorize that terminology. I'm not going to make you regurgitate it on a quiz or a test. But it does help us when we're working through assignments and questions if we can use that terminology. And then you'll know if I say track in your head, hopefully you can say, oh, that's the actual path of the airplane, as opposed to the heading, which is just the direction that the nose of the plane is pointing, right? Flying crooked. So, like boaters, we're going to look at a couple different scenarios here. The first one we're going to do is a crummy pilot. And here's some information we're going to use for this example and the next video as well. We're going to have the plane's airspeed at 200 kilometers an hour. We're going to have the wind blowing at 50 kilometers an hour to the west. So it's coming from the east, but think to the west. That means to the left. Fuel consumption you don't actually need for this video, so don't worry. And the map scale I'll walk you through in a moment. We're actually going to find something on the map. So we're going to start with crummy pilots. These are pilots who don't account for the wind. They think that on a windy day, they can just point their airplane at their destination, take off and get there. It's not going to work. So we have a float plane leaving Pritchard, British Columbia, everybody's favorite place, and they are trying to fly at 46 degrees south of east, and they head out for 46 minutes. We're going to imagine that maybe you're working at an airport, like in Kamloops, we'll see on the map that's nearby, and you get maybe a mayday call. Hey, my name's Jimmy. I'm lost. I've been flying this plane. It can go 200. The wind's blowing at 50 kilometers an hour to the west. I tried to go 46 degrees south of east. I'm lost. So we're actually going to go on a little rescue mission and find Jimmy on this map and tell him, well, here's where you are, and then he can figure out how to get back. Maybe again with our help. So what you need to do is switch over to the airplane assignment. And we need to find Pritchard. Maybe you've driven by it. It's right here. So that's where he's leaving from. And we're going to find this crummy pilot on this map somewhere. So we're going to start by drawing a nice big diagram. And like big. Like it should take up most of this page big. So Jimmy is flying 46 degrees south of east. So that means down and to the right. That also means that I probably want to start my diagram in the top left-hand corner of my page so I can make it nice and big. So I want us to start with a compass crosshair or compass rose. That's going to represent Pritchard. I'm just going to put a P for Pritchard. And Jimmy points his plane 46 degrees south of east and takes off. that plane can go 200 kilometers an hour. So you don't need a protractor to measure, but get the line at maybe something close to 45-ish, 46-ish. So I'm going to draw something like that. And now we really carefully want to label that 46 degrees south of east. And remember that south of east means pushing towards the south, which means the 46 is going to go on the top side right there. And I actually want to go a step further, and I want to show myself that the 46 is that line. Because we're going to see there's another line that leaves from this Pritchard dot, and I don't want to get them mixed up as to which one is actually the 46. So draw that second little arrow in there. So Jimmy's trying to get here. That's the destination. I don't know what it is. It doesn't tell us, but that's where he's trying to get to. So he aims at that spot. He's forgotten that it's a windy day. He points his plane at 46 degrees south of east, bangs the throttle, and we were told the plane can go 200 kilometers per hour. Now there's a problem. I'm going to go draw another compass rose here. The problem is that as Jimmy was flying along that vector, he was being pushed by wind to the west, which is that way, at 50 kilometers per hour. And that means that Jimmy actually flew along this vector. He pointed his airplane along the blue vector, and it was pointing that way, but it flies crooked and it actually flies along this red line. So we want to put these compass crosshairs in all the corners. It's going to help us see something in just a moment. And now the two things we want to find for this triangle is the actual speed of the airplane, also known as the ground speed. And we want to know the angle up in this corner, always the corner where you left from. That is called the drift angle. How many degrees did we drift off course? Now, I can tell you this is kind of cool. A Crummy pilot always starts with cosine law. Every single time. C for Crummy, C for cosine law. Now, before you can run cosine law, you have to get an angle inside of the triangle. And right now we have no known angles inside of our triangle. So what we need to do is go back to something I think you've learned in math before, where if you take two parallel lines and you draw an intersecting line through, we've kind of made a Z shape in here. And something called alternate interior angles, says that those two angles, the two corners of the Z, will be exactly the same. So what I need us to do in our picture is find the Z with the 46. And you have to be really careful here. Hopefully you've labeled this really well. That's why we draw big diagrams with compass roses and we use our ruler. We want to be able to see that 46 is along the blue line and not the red line. And that means our Z, which I guess is backwards, but that's okay, is this one. Because this little blue arrow, which is very, very handy, tells me that's the corner of the Z. That's the 46. That means this corner down in the bottom is also going to be a 46. So I'm going to take those lines out of there. This corner, also 46 then. And that's perfect because if I want to run a cosine law to solve for V, I need to know the angle opposite that. I've got it. So let's try that out. V squared is equal to, it's not the longest side of the triangle, but it doesn't matter. Cosine law doesn't care about which one is the longest. So V squared equals 200 squared plus 50 squared. The formula's on your formula sheet too, by the way, if you need it. Minus 2 times 200 times 50 times cosine 46. It's an easy equation, just takes a while to write it out. Let's bang that out in the calculator and see what it gives us. Again, should be able to type all of this in your calculator in one step and then square root it maybe as a second step. So there's the number before the square root. I'm not even going to write it down. Take the square root of that. 169. 169, that's kilometers per hour. That fits with my triangle because I can see that side V has to be shorter than the 200, so that's great. And that is the real speed of the airplane, aka the speed compared to the ground, aka the ground speed. So crummy pilots, you'll always start with the cosine law to solve for V. Then we have to go and get theta, that unknown angle. And if I label my diagram and say, hey, that was 169, now you can say, hey, look what we've got. This is good. We've got an angle and its opposite side, which means we can use sine law now to solve for theta, because opposite theta is a 50. So let's try that out. Maybe I'll take these out. Don't put them in yours. It gets a little jumbled. We've got the sine of 46 over 169 is equal to sine of unknown angle theta over 50. We can do the cool little cross multiply and divide. That means multiply diagonally, divide by the leftover. And then you will have to second function the decimal that you get. Don't forget about that part. And if we try that on the calculator, pardon my slowness while I do this. There's the decimal, second sign that answer, 12.3 degrees. Just to give you a hint, you're typically looking for a number between, 4 and 15 degrees is usual for Physics 11 questions. So that seems to fit quite nicely. So that's 12.3. Now that number on its own is how far we've drifted off course. But if this pilot is lost and stressed out and doesn't know where they are, you don't want to just tell them that they've gone off course by 12-ish degrees. You want to give them the actual angle that they flew at, which is called the track. And in our diagram, if you want to find the track, I'm just going to extend out my compass here a little bit. The track would be the angle to the red dotted line. So this angle all the way to there. That's track. Because the airplane actually flies along the red line. So I want to know the angle to the red line. And in order to get the track, this is where, again, a big well-labeled diagram is really going to help out. You can see here that it was 46 to the blue line, and then we've stacked this 12.3 degrees on top. So I'm actually going to add those two things together. 46 plus 12.3. which is equal to 58.3 degrees. And that's the same direction as before. It's still south of east. We need to make sure we put that on. There you go. Another very important number for us. Now, another additional calculation is figuring out how far the plane went in that 46 minutes that they flew. Yeah, Jimmy was flying for 46 minutes. So we use D equals V times T. You always use for pilots the real velocity of the plane, the ground speed. So you don't have to remember things being parallel like we did with boaters. It's just take the velocity that you solve for. That is in kilometers per hour. I'm going to show these units just the first time so we don't forget. So I can't take that and multiply by 46 minutes. Because minutes and hours don't play nicely together. So we will have to take the 46 minutes and divide by 60 just to get it into hours. So 169 times 46 divided by 60, you can do that all in one step, is, let's call it 130 to get our 3 sig figs. So 130 kilometers. That's in real life. And we have to figure out, what does 130 kilometers in real life look like on this map? There's a scale to the map, right? And you've maybe done this before in social studies, and it can sometimes be a bit of a pain. But I've made it really nice for this map. I lucked out. The map scale is that 1 kilometer in real life represents 1 millimeter on the map. So 130 kilometers in real life means 130 millimeters on the map but it turns out you're probably not going to measure with your ruler in millimeters. Typically you would go into centimeters, so divide by 10. That's going to be a 13 centimeter long line. And now the fun part is we actually get to locate this person. So if we go to the map, there it is. We want to draw a compass rose on top of Pritchard, like that. And we know that we're flying south and east, which is just generally down that way. What was it, 58.3 degrees south of east. So you need to grab your protractor. You're actually going to spin it upside down. So I can't show you show you me doing this on the screen, but you want your protractor to be like that. And you're going to look for 58-ish. And what I want you to do is make like a little mark on your page, just off of the 58 degrees. So I'm going to take that away and actually do this. Again, I'm doing it for real right now. You just can't see it. So 58-ish is going to be somewhere right about. My protractor's kind of big. Right about there. And then, once you've got that mark at 58 degrees, you need to draw a line that is 13 centimeters long. And again, you can't see me do this, but start right on top of Pritchard, grab your ruler, and I want you to drag a line right through that 58 degree mark that you made and make the thing 13 centimeters long. So something like that. And hopefully it's a place that you have heard of before. Maybe you've been there. You should hit Big White Mountain. So we've actually located Jimmy. He's at Big White Mountain. We're not going to worry about actually telling him how to turn around and get home, but we found him. Sometimes students will say, well, how close do I have to get to that for it to be a correct answer? And I'd say if you dropped a toonie on top of Big White Mountain, do you hit the toonie? And the toonie would probably be about this size. So if you can get sort of within that circle, I'd say that's great. You found them. So that is Crummy pilots. Kind of fun. What I want you to try, you've got a few of them on this assignment. That's part A. So try these two right here. There's two of them there. You can just repeat that procedure with different directions and different numbers and do a little rescue mission ×2 off of that map. Some hints when you're doing this. Big diagrams. And when I say big diagrams, I'm talking like one per page. That's all you should be able to fit. One big diagram and its associated calculations should fill up one whole side of the page. I also want you to put arrowheads on your vectors. That's important. You have to know which direction things are facing. If there's just a line, it could be going in either direction, either end of the line. And then the third thing that'll really help you out is to put those compass roses in every corner. And you need that so that you can see those Z's, the alternate interiors. If you need some help with any of this, please get in touch with me. Happy flying.